in part B of number 10, it wants us to calculate the action force of box A on box B. And so if you recall, we have our initial diagram where we have our three boxes next to each other. And so what I'm going to do is draw the free body diagram, firstly of box A. Right, it's the furthest on the left. So box A, the forces acting on box A is the force of gravity, the normal force, the applied force, and the box that B is pushing back on A with. So I'm going to call that FBA. Right? Force block A is getting pushed into box B. So that means box B is going to have a reaction force in the exact opposite direction on box A. Now let's draw the free body diagram of box B. So box B, and there's also our force of kinetic friction on box A. Then on box B, we're going to have a force of gravity, our normal force. This is the force that A is putting on B, right? And ultimately, this is the force that we're looking for. We're looking for the action force of box A on box B. So that is that force. Coming backwards, we're going to have a force of kinetic friction. But also remember, box B is right up against box C as well. So box B is going to be pushing in. Box B is going to be pushing into box C. So box C is going to be pushing back on box B. And so there's going to be a force that box C is putting on box B. And so let's get our last free body diagram, right? So on box C, we have our force of gravity on box C. We have our normal force. We have our force that block B is putting on C, right? So that's the equal and opposite force of that one. Coming backwards is just our force of kinetic friction, because there is no, there's not a box D, for example, for instance. Okay, so fundamentally we're looking for this force AB. However, if we were going to use this free body diagram to calculate it, what we would have to do is figure out the net force acting on this block, right? So just to quickly walk through what that would look like, our normal force and our force of gravity are equal and opposite, so they'll go away. This force of kinetic friction we can calculate because we do have the coefficient now. However, this force that block C puts on block B, we would have to figure out from this free body diagram, right? We would have to work through here in order to figure out what this force is, so that we could then say that this force is equal to that force, and then we know that the net force is going to be equal to the mass times acceleration. We know the acceleration, we know the mass, so then we could rearrange and find this force. However, that is quite a lot of work. There is a simpler way to solve this problem. We know that this force that A puts on B is going to be the exact same as the force that B puts on A, right? The magnitudes of the forces will be the same because they're Newton's third law forces, right? Action, reaction. And so if we're able to calculate this force that B puts on A in this first block, then we'll be able to work through it, and we'll just know once we find it that it is exactly equal to this force. And so that's what we're going to take. Instead of trying to find it directly by calculating force CB and then working backwards all the way to over here, we're going to just find the force that B puts on A on this first block and realize that it's exactly the same force as this one. So let's look at the information that we have for block A a little bit more closely. We know that the net force acting on this is going to be equal to the applied force plus the force that B puts on A, which is our goal, right? This is what we're looking for. Plus the force of kinetic friction, plus the force of gravity, plus the normal force. These go away, and so we're left with the net force equaling the applied force plus the force that B puts on A plus the force of kinetic friction. Again, each of these we can break down, or we already have the number for. So we know that net force is equal to ma by second law, and the mass and the acceleration are both quantities we have. We also know that the applied force is just going to be equal to the applied force given to us in the question, which is 250 newtons. So this is going to be equal to 250 newtons. Again, being careful with direction, right? So east is positive. So our net force is in the right direction because it's accelerating in the right direction. This applied force is in the east direction. Our force that B has on A is going to be in the negative direction, but we're going to keep this vector symbol above it, so we're not going to change the sign yet. And then our force of kinetic friction is going to be equal to minus mu k mg, right? Because the normal force is equal to the force of gravity, which is equal to mg, the magnitudes. Okay, and so now we can start putting some numbers in. So our mass of block A is 55 kilograms, and the acceleration given to us in the question is 1.2 meters per second. This is going to be equal to our applied force, and we're going to subtract off our coefficient, our frictional force. So we determined that this coefficient was 0.15 in the last question. The mass of the block is 55 kilograms, and G is 9.81. All right, and so now it's just algebra to solve for this. So I'm going to rewrite this. This is going to be equal to 66 minus 250 plus 80.9325, and that's going to be equal to the force that B puts on A, and you put that into your calculator and you get minus 103.0675 newtons east, which means that the force is to the west, which is what we expected, right? We expected this to come out negative because it's pointing to the west. And so with significant figures, we're going to round this to two significant figures. So we're going to write this as 1.1 times 10 to the power of 2 newtons west. And so our final answer, right, because we're fundamentally looking for this force, not the force that B is putting on A, but the force that A is putting on B. So FAB is going to be equal to 1.1 times 10 to the power of 2. Sorry, 1.0. 1.0. I rounded it correctly. 1.0 times 10 to the power of 2 newtons